right, hello everybody. Welcome to day 4 of the main track of the technical program here at AAAI. We've had a wonderful time here. Many great events, many great speakers, and you know it's such a richful conference that we're glad that you're joining us here, given all the stimulation that we've had. For day 4 of the conference, we're going to we have a number of great talks as well as our closing session. So please come to Derek Lee's talk later today, as well as our closing, where we'll give some overview and some of the awards that we'll present. But now we're going to start with our first plenary talk of the day for the Patrick Henry Winston Outstanding Educator Award. And like to bring to the stage Nargis Narouzi.
Good morning, everyone. My name is Nargis Narouzi, and I'm a faculty member at UC Berkeley. I'm here in my capacity as AAAI chair, presenting here to you this year's AAAI Patrick Henry Winston Outstanding Educator Award. This award recognizes educators who made major contributions to AI education that provides lasting impact that benefits the AI community and the society. This year's recipient, Alan Mackworth and David Poole, didn't just produce a widely used AI textbook, they also built an entire infrastructure around it. They provided Python code that the students could simply run and learn more about AI. And they also created an entire web-based infrastructure for instructors that they could teach AI interactively. Today, David Poole is accepting the award on behalf of both recipients. Please join me in congratulating Alan Mackworth and David Poole and welcoming David to the stage.
All right. Thank you very much. It was a great honor for us to receive this award named after the great Patrick Winston. All right. Unfortunately, Alan cannot be here. He was an invited talk at the conference in Toronto at the same time, and it was a little far to go from Toronto to here in a very short period of time. What I'm going to talk about today is things every student of AI should know. And Alan and I still think of ourselves as students of AI. We're still learning what we can. We've picked one of these things that students should know. The essence of intelligence is appropriate action. And these other parts in the parentheses here, thinking, reasoning, learning, and action, and language, all go towards action. That's the reason we do these, is because of action. So that's one of the things that we should all know. Okay, so we've made, this is the 4 books that we've written on AI. The first one was from, published with Randy Gable, with Alan Mackworth and I, from Oxford University Press from 1998. And the last 3 were published with Cambridge University Press. And the full text is online. So everyone in the world, we've tried to make it as accessible as we can. And Cambridge University Press were very kind in letting us put everything online. So here's the website for the book. And there's not only the resources and slides, we have the complete text online. So if you go to any particular part, you know, everything, you know, the whole text is online, figures, diagrams, and everything else. Okay, so you can use it, right? So freely available. So we also have, over many years, almost 25 years now, we've had, well, it stopped now. We've had over 25 years, we've had students, undergraduate students, building over summer tools for building AI tools, and that's this AI space. And we've had a number of these that are used all over the world. Unfortunately, they're not very usable now because of Java security. When we started, Java was promised to write once and run everywhere, and it would handle all the security for us, but that did not come to pass. All right. And finally, we've got this AI Python. More recently, it's runnable pseudocode is the best way to think about it. So it looks like pseudocode. You can read it like that, but you can actually run it and do this. And there's basically every algorithm in the book is in there: searching, constraints, propositions, reasoning with uncertainty, causality, planning with uncertainty. All of these are in there. some of them are actually quite efficient, like the searching ones are actually pretty good. Some of them are really bad. Do not use the neural network code for anything except playing around and learning how, neural networks and different optimization algorithms work, because it's thousands of times slower than, it's not compiled to a GPU, it's all just nicely interpreted single core. But some of them are actually quite useful. So some of the others are actually quite efficient, some of them are quite useful. All right. So let's get on the topic of this book. Before we start, you don't think you're going to get out in my class without being active participations. I want to know how humans evolved intelligence. You're going to ask to vote on one of these. A, it was selected when finding a suitable mate, just like the picture of a peacock I took, evolved these fancy feathers because it was the mates chose feathers so it was attractive to them. B, it enabled behaviors that helped humans survive and flourish. C, it enabled them to spread gossip and information. D, it enabled people to have deep inner thoughts. Or E, it was just random. So why did humans evolve intelligence? Who thinks the answer is A? Put your hand up. Who thinks the answer is B? Put your hand up. All right. Who thinks the answer is C? Put your hand up. Who thinks the answer is D? Put your hand up. And who thinks the answer is E? Put your hand up. And who doesn't think? Put your hand up. All right. The mode was B. So some people believe the title of this talk, although everything else got chosen here. So let's try and convince you that A is the right way to think about this. I'm going to give an overview of lots of AI topics and things that try to understand how intelligence works. So things that lots of people have encountered don't know. So that was the topic of this talk. So what we're going to do is talk about agents. What should an agent believe? Then what should an agent do? And where do goals, values, and preferences come from? All right, let's talk first about agents. We've defined artificial intelligence as a synthesis and analysis of computational agents that act appropriately. So we're interested in action. There's the acting in here. The computational there is because we want to build systems on it. We're not doing psychology or economics or other fields that think about action. And we're both synthesizing and analyzing these. And acting appropriately means acting appropriately given the environment that the agent is in. So here is a picture of our view of agents. Agents carry out actions in environments. The only thing, then, what's the input to an agent? Here's the agent as a black box. The inputs are what the agent observes about the world, but also as a history of past experiences, sometimes put in separately. But that's not all an agent needs. An agent needs some prior knowledge or bias, but it also needs goals and preferences, and it also depends on its abilities, what is available to the agent to do. So now we have these goals, and now we have all of these, and this is the only thing that's available to an agent. All right, so now let's think about what happens now. So agents act in time. So here's a diagram we're going to do. It's a bit complicated. I'll explain it in a minute. You can think of time going across the x-axis in here. So the bottom one is the state. The environment state goes from state time 1, 0 to 1 to 2 to 3. So the state at any time depends on the previous state and the action of the agent. So the only way to affect the environment is to act. And that's why acting is so fundamental to what agents do. So this is the state at any time, depends on the previous state and the action. The actions, how does an agent get to decide what to do? Well, it only depends on the agent's belief state, what's in its mind, and what it observes. That's the only thing available to an action. What the agent observes depends on the state of the world, their actions, and sometimes they observe some reward signal. An agent's belief state, well, what does an agent believe? Well, all you get to do is observe the world. So all an agent gets to do is observe the world and has a history of beliefs. So it doesn't get to observe the state of the world. It doesn't really get to observe anything else. All it gets to do is observe the world and has to work out how to update this. And finally, the reward function here, we're going to assume depends on the state of the world and the actions. So this is sort of an all-encompassing view of agents in time and overviews how we're going to view intelligence. Okay. So the first question is, what should an agent believe? So we're going to talk about this belief function. How should an agent believe based on what should an agent believe based on their previous beliefs and their observations? All right. So what if the environment's not fully observable, which is the first assumption we got? We're going to generally assume it's not fully observable. It's only fully observable in very restricted game-type domains. So first is, when an agent does not know the outcome of an action, it's gambling, and probability is the calculus of gambling. So we're going to, probability is the foundation of what we're going to do. It was frowned on for a long time in artificial intelligence, but it really is important for acting and decision-making, because we're always gambling. And if you want to know, for learning, so if you want to think about, we want to describe conditional probabilities, learning a conditional probability from data is called supervised learning. And so we're going to, whenever you see a probability, you can think about, oh, I can learn this from data, right? So probabilities here, we can think about learning from data, and just supervised learning gives you probabilities. And there are lots of different representations for conditional probabilities. There's the ones we see we first learn probabilities, as well as decision trees, logistic regression, noisy OR, gradient boosted trees, and neural networks with sigmoid or softmax output are all representations of conditional probability. So if you think about this, if you have lots of data, you can use gradient boosted trees or neural networks whenever you see conditional probabilities. Think, oh, I can learn those, right? So you want to think about it in those terms. And there's a common task, common way that people think about learning is doing end-to-end learning everything at once. And this is sort of gets trendy, and sometimes it's now seems to be pretty trendy, although it's maybe going down. All right. So let's give a running example. So here's a running example of a diagnostic agent for human diseases. I'm going to assume the belief state of an agent is a diagnostic agent is the joint probability distribution of the patient's diseases. So it's, in my mind, I'm thinking, what's wrong with this patient? The observations the agent's going to make are the symptoms, the test results, all the electronic health records. So I want to bring every piece of evidence available to me to make this decision. So I'm not only just going to look at, I'm going to look at very heterogeneous data in electronic health records. It includes x-rays and everything else, all the tests they've done, all their whole history. And then I want the belief state update. Well, I want the probability of the belief is the probability of diseases given the symptoms. So that's what I'm interested in. So an example is the probability of hepatitis given chills and fever. And if you think about this for a moment, the probability of hepatitis given chills and fever also depends on whether you have the flu, the influenza. So you could use end-to-end learning to learn this conditional distribution. And you're probably saying, oh, I know how to do that. So everyone's saying, I know how to do that. However, it's a bit tricky because it probably depends on the location. So in Cambodia versus Canada, in Cambodia, hepatitis is very common. But in Canada, the flu, influenza is very common. So you get different probabilities if you apply it in Cambodia versus Canada. Or if you just ignore them, you get another probability as well. It also depends on the time of the year, the prevalence of the flu, how prevalent, not only malaria, you have to worry about the flu. You have to worry about whether patients are vaccinated against the flu and or hepatitis, the sickness of contacts, about whether the person's been close to someone who's traveled and whether they're sick or not. So all of these things this probably depends on so many different variables in the context. You want the probability of the diseases given the symptoms and the location and everything else you can possibly imagine that is relevant. And the first question we look at is, do we just need to learn with more data? Do we just need more and more data in order to learn this? All right. First of all, there are lots of domains that have lots of homogeneous data. Sensor networks, images of cats. There are lots of images of cats. There's lots of text. There's lots of DNA sequences we can learn from. Or we can generate arbitrary amounts of data. There's games and programs and other things where we can just generate arbitrary amounts of data to do. And it's usually better to collect more data than provide more knowledge for these cases. So if you have a domain like this, then just collect more data and just apply it to straight machine learning. Machine learning is a solved problem, by the way. So you can just do this. It's called a bitter lesson for some reason that I never understood. So here's an example of where you can't do this. So let's try and think of examples where we can't do this. We can't always do this. So SNOMED CT is this healthcare terminology. It's a standard healthcare terminology. It has over 360,000 concepts in multiple languages. Okay. Over 100,000 of these are diseases and other ailments. 100,000 is an interesting number because 100,000 squared is 10 billion. Okay. There are lots of people with multiple diseases, so you have to worry about disease interactions. And there are about the same number of pairs of diseases as there are people on Earth. Okay? So if it was spread out evenly, if you could actually cover all the cases, you'd have one case for every pair. But of course, it's not uniformly covered. For nearly all pairs of diseases, there is inherently no data, right? We don't have the choice, let's collect more data. There's not enough people and too many diseases. Okay. If you had 40 diseases, there are more combinations of diseases than people have ever lived. So we can't possibly just collect more data about different combinations of disease and say, let's just get more data. There just aren't enough people who've ever lived. And that's only with 40 diseases. So the combinatorics is going to kill us if we just try and build. And this is we just can't get the data. There's just no data. All right. There's not enough there can't be enough data to learn disease interactions using only data-hungry approaches. All right. And the same argument goes with symptoms. There are about 100,000 symptoms, and so different combinations of symptoms that people have. There just aren't enough there's just not enough way to get the data. Okay. So how do we do this? So what do we do here? How can we avoid this combinatorics of the probability of disease given the symptoms and locations of everything else? Well, there's a computer science solution. If you've ever done a computer science degree, you know the most important thing you've ever learned in computer science is to solve a complex problem, you break it into simpler problems. Okay, if you only learn one thing in computer science degree, it's this. All right, so let's just break down complex problems into simpler problems. And you want modular components. So the components can be learned separately and combined. We can combine these problems separately. We also want transportability. We want the components to be stable when changing locations, times, and populations. All right, put up your hand if you think the future is going to be just like the past. All right, no one. So you should be suspicious of any people who use a test set that's a random subset of the data, because that's not how the world works. You've got to predict the future from the past, because the future is not going to be like the past. So you've got to be suspicious of all these people who just say, well, let's just learn, let's just use that. Oh, it really works well, because if I take a random subset, it works in our test set. So let's work out how we can solve this problem. Here's Bayes' rule. The probability of diseases given symptoms, the probability of symptoms given diseases, and the probability of diseases. And everyone's familiar with Bayes' rule. And why is this of interest to this here? Well, the idea is that the probability of symptoms given diseases is stable across time, right? The symptoms of diseases don't really change. Maybe the disease transforms into a new disease. But it also doesn't depend on the population. It doesn't depend on whether people have traveled, whether my friends have traveled to some place, what my symptoms are as this disease. So this is going to be transportable. And think about what happens when a new virus arrives. When a new virus arrives, if you do end-to-end learning, you never get enough data for it. Everyone's dead by the time you've got enough data. But what we can do here is nearly everything still remains the same. We just have to model what are the symptoms of this disease and how prevalent is it? What are the symptoms of having this new virus? And then you're going to model the prevalence of it. So we split it down into modular. So this is why we want to think about reasoning about uncertainty in belief and probability theory. So we can think about the probability of diseases given the symptoms, the location, and whether my friend's sick is proportional to the probability of the symptoms given the diseases, remember, which didn't depend on the location and whether my friend was sick, times this. And we end up with these representations of uncertainty. So belief networks or Bayesian networks or directed graphical models, these represent conditional independence. The arc means depends on, and they're modular. You can learn them separately. Oh, Okay, so they're both modular and transportable. So we're trying to build these models so that these are stable, so that the probability of symptoms given diseases doesn't depend on all this extraneous other stuff. We're going to work out where the friend's sick, how that affects whether I have this disease. So we want modularity is going to be important for building systems. Okay, and we can learn this from data. So whenever you see conditional probabilities, think neural networks if that's your inclination or something else. All right, here's an example of a fictional probability of the probability of hepatitis and the probability of giving hepatitis vaccine. And the number I want you to look at is this number on this bottom right-hand side here, is this 0.028. And I want to say, let's give the populations, let's condition on the fact that hepatitis vaccine is true. And all of a sudden, if you do that, you'll find the probability of hepatitis goes up. And you think, what? How can that be? If I give people hepatitis vaccine, surely the prevalence of hepatitis should go down. But the thing is, this is not what this is measuring. This isn't whether you give them hepatitis, whether you give them the vaccine or not. This is if I observe the people having hepatitis. If you want to work out what happens when you give people hepatitis, if you give them the vaccine, well, you want this other one. You want the probability of the hepatitis in Pearl's notation given you do, and all of a sudden it goes from 2.8% to 1%. Okay, so in this model here, so the observations of the world give me the exact opposite correlate effects than the correlations do. How can that be? Well, here's the model I gave. Whether you have a hepatitis vaccine is dependent on whether the hepatitis is endemic where you are, and whether you have hepatitis depends on whether the hepatitis vaccine and hepatitis is endemic, right? If you observe the hepatitis vaccine is true, then the probability that it's endemic goes way up. People only get hepatitis in places where it's common, and that's why you're going to get this answer. If I do give you hepatitis independently of whether you have hepatitis vaccine, then this probability goes down, okay? The causal models here predict the effective outcomes, and this hepatitis endemic here is a confounder. By the way, this is all open source code that everyone can use and play with and build these systems. But the point is, from these observations, we cannot work out the effective actions. That's the next thing you should know. So the effective actions cannot be learned from observational data. You cannot observe the world and it tells you what happens when you act, right? It's a fundamental problem with just saying, oh, let's just get more data. It doesn't tell you what happens when you act, okay? You have to interact with the world to determine the effective actions. Children have to play with the world. You can't just sit them in a box and let them watch TV and expect them to know how the world works. It doesn't work like that, all right? You need a real body to carry out experiments, and it's possible to think about having all connected sensors in the world as long as you can control the actuators. So it's possible to not only think about let's just have one little robot, but let's think about everything in the world, just like large language models. So let's get all the text in the world. Maybe we want lots of different agents to play with the world and do this. So you could have everything together in the action of trying to do this actuator, of trying to learn how the world works. All right, here's another example of what we might do. So here's a placebo. So here's a drug. Now, the green is whether they're well, the orange here is whether they're sick or not, and the pink is whether they're very sick. This drug, all it does, it makes sick people sicker, and it makes some of them so sick they drop out of the study, right? That's what this dropped out does. Now, if we ignore the missing data, so if you ignore missing data, right, what happens? We're going to remove all the part that's crossed off here, okay? Then what happens is a higher proportion of the took drug are well than the placebo, fewer are sick, and fewer are very sick. This looks like a great drug, all right? The drug looks really good, okay? So who, when they're looking at a data set, considers all the data that's not in the data set? Put your hand up. Oh, I thought there'd be someone at least. You're getting misled. If you only look at the data you have, you're getting misled because you have to work out where the data comes from, right? You have to work out, we've had You've been told this a while ago. We need to worry about the provenance of the data. Where does it come from, right? You have to worry about that, right? If you just accept the data as it is, you're going to get the wrong answers, okay? So you have to model and find out why data is missing. If you look at clinical trials in medicine, the reason they're so expensive, one of the reasons they're so expensive is you have to trace all of your missing data and find out what actually happened to the person, okay? All right. That's another question for everyone. What's the real world made of? Is it A, features or random variables, B, words, pixels and phonemes, C, entities and events such as plants, people, diseases, talks and conferences, or is there a real world? Who thinks the answer is A? Put up your hand. Who thinks the answer is B? Put up your hand. Who thinks the answer is C? Put up your hand. All right. Who thinks the answer is D? All right, a few people put up 2 hands, good. All right, seems like C is actually I think it's the majority here. If you look at the popular press, you'll think the world's made up of words, pixels and phonemes. If you look at machine learning conferences, you'll think the world's made up of features or random variables. However, nearly everyone here thinks that the world is not made of that, it's made of entities and events. Have you ever been so funny about why don't they talk about things in AI conferences and machine learning conferences? Have you ever wondered that? Yeah, well, I have. All right. Here's a nice quote from Steven Pinker from How the Mind Works. The mind is a neural computer fitted by natural selection with combinatorial algorithms for causal and probabilistic reasoning about plants, animals, objects, and people, right? So mind is sort of tuned to think about objects and things, okay? And so we ought to think about objects and we think about things. Okay. All right. So there's a whole field that's talking about things, and that sometimes appears here. In fact, so it's relational learning, is learning models that make predictions about entities, things, objects, including events. Their properties of things, relations amongst entities, whether something exists, so given a description, whether there actually exists something that fulfills that description, and identity, whether the person who comes in today looking for drugs is the same person who came in yesterday. Okay. This field has lots of different names: statistical relational AI, relational probabilistic models, and logic learning. I just want to tell you 2 things that everyone should know. So here is a relation, and this is a typical relation. There's the patient, the particular patient with this identifier took the test with this identifier, and the technician who did the test had this identifier, and the result was positive. We finally get a number that we can actually interpret as a number. It's 0 or 1, and the date time, of which in here is some other inclination of the date and the time. If you look at relational data sets, they typically contain lots of identifiers. These are typically integers, but they don't mean integers. They're just arbitrary identifiers. If you look at a student services database or an airline reservation system, nearly every number in there is an identifier. Tabular data, which we learn about in machine learning courses, is this very degenerate type of relational database that sort of ignores identifiers. Okay, so it ignores these numbers that just identify things. People usually work hard to create a tabular data set that doesn't include identifiers. Okay. So we could actually think about, people talk about knowledge graphs. So subject, verb, object triples form knowledge graph. And there's a subject and the verbs, subjects and objects are the nodes, and the verbs form the arcs in these. Okay. And if you're given a table, the way to construct a knowledge graph is you're going to use row column values. So you're going to think about this row, this column, and this value. The row is either a primary key if there is one. So if there's one value that identifies the row, you should use that. Otherwise, you're going to construct an identifier for the tuple. You're going to reify it. It's called reification. Reify is just a normal English word that means make into an entity, make into a thing. Okay, so we're going to do that. So you're going to practice this sort of identity. You're going to construct for the first row, you're going to construct an identifier for it. I just concatenated a whole lot of things to make this identifier. And the patient is this particular patient ID, and the result is 1. Okay. What you should know about this is the number of triples for these reified tuples, is inherently very small. There's a number of columns. If you have a very data-hungry approach that wants lots of data about anything, then it's going to fail on these, okay? Because so in Wikidata, I estimated that over 98% of entities are reified with 10 or fewer tuples. And as you get more and more data about something, you actually get more and more reified entities, and you get higher proportion of them have very few entities in them. So when you're learning about these things, nearly everything has hardly any information about it. Okay, so we're ending up with, although we have huge data sets, we end up with very small numbers about any individual, any entity. All right. Next topic that everyone should know about is how do we reconcile probabilistic models? We build probabilistic models, and we build neural networks and all of these other things that are determined on features and random variables and knowledge graphs. How can we reconcile these things? All right, so here's the answer. Functional verbs or properties, these when they're functional, when for each entity there's a unique value, you get a random variable for each subject-verb pair. So birth year, so for each person there's a unique year, and the value here is some integer for what year they were born in. Another functional property is birth mother. So for each entity, we're going to say who is their mother is a value. So the set of random variables is a set of all people. And if you think about birth mother, you can't have an identifier for every person because you end up with an infinite chain of birth mothers, and you need infinitely many identifiers, and after a while, it's all just fiction. The other one is to have, for non-functional verbs, you need a Boolean random variable for each subject, verb, object, triple. So if you work has streamed as a relationship between a person and a song, you're going to talk about, you're not going to say, what's the probability of that distribution over songs they've streamed, because they've streamed lots of them. There's no probability distribution. You need the probability for each person and for each song, whether they've streamed it or not. You could talk about the probability of that. So these end up with sort of called relational probability models, and they represent how these random variables interrelate independently of the actual identities. So there's a whole lot of models in this field that work independently of the actual entities. When I build a model, it doesn't really depend on the actual identities. And it's interesting, this independent of the actual identities has lots of different names in the field. It's logic variables or universal quantification, because we're doing it for all. Okay, it's called lifted or exchangeable in statistical notions. In neural networks, it ends up being called parameter sharing or weight tying or convolutional, as in graph convolutional neural networks. Okay, so it means that you have this value that you can use for all instances. Okay, and these are all sort of the same abstraction of doing this. You're going to represent it independently, and you're going to use it for all instances. Okay. All right. Let's now talk about determining truth. Determining truth is a problem that everyone talks about for AI these days. However, it shouldn't be a mystery how to determine truth. People have been doing it for millennia, right? We know how to determine the truth, right? It's subject of science. It's what science does. Science determines the truth. Criminal law determines the truth, right? We know what to do, right? We need to consider all relevant evidence. You don't want to ignore any. We want to build hypotheses that explain the evidence. This sounds a lot like machine learning. You want diverse sets of hypotheses, because there might be lots of different ways things have happened. But then you want to be really critical. You want to be really skeptical about this. We want to sort of say, is there anything that could possibly do this? Could possibly be wrong with this? In a criminal trial, people have advocates for the defense, and they try and beat all your hypotheses. We need to do that. And what happens is, with enough independent evidence, the truth tends to pop out. It's something that is rather amazing, because the truth fits the evidence, whereas other hypotheses won't quite. So if you think about, if you actually do this, if you look at an image of a cathedral and you want to work out what it is, well, it's just lots of weak evidence compared to that says that only this image could only be this particular cathedral because it's the only thing that fits. Okay, and there's lots of these things that are settled. It's sort of relativity, molecules, evolution, vaccines. Scientists don't talk about it because it's accepted. The reason it's accepted is because the evidence is overwhelming for them. The difference is the law has to make binary guilty or not guilty decisions, but scientific hypotheses are always open to revision. And Jaynes has said probability is the logic of science, and for all sorts of reasons you want to think about science as using probability, much as we've seen so far. And science requires physical experiments acting on the world to determine how the world works. All right, so you need to actually act in the world, which is again, comes back to the first title of this talk. And you really need, and as we've seen in a couple of talks, this invited talks, this conference, you need to keep track of the provenance of all the data. You need to worry about where the data is from, because this only happens with independent evidence. And statisticians sort of assume that evidence is independent. They just say, oh, let's build this and assume we get independent evidence. It hardly ever is. It's a really difficult, and there's very little work. There's lots of work on giving the provenance of data. There's very little work on, is this data, given all its provenance, actually independent? Or can we combine it together? So in here, while there's been lots of talks on science, I'm claiming that everything should be science. We can learn the science of what I should eat for dinner tonight, and we should have hypotheses about it and build them up. All right. Next topic is, what should an agent do? So next part is about what should an agent believe? What should be in the belief state of an agent? Second one is, what should an agent do? It's one of my favorite quotes. It's from Alice's Adventures in Wonderland from Lewis Carroll, who, by the way, was a logician by trade. Alice went on, would you tell me, please, which way I ought to go from here? That depends a good deal on where you want to get to, said the cat. I don't much care where, said Alice. Then it doesn't matter which way you go, said the cat. If you don't have preferences, it doesn't matter what you do. Okay, so if you don't have preferences, who cares what you do? The only reason for doing something over another is because of preferences. Okay, so here's the here's the basis for preferences in nearly all of AI and economics, etc. So it's utility theory. Here's the utility theory in one slide. Actions result in outcomes, and agents have preferences over outcomes. So that's the basic assumption. Let's consider this question. Would an agent prefer outcome O, some outcome, to a lottery? And the best outcome with probability P and the worst outcome with probability 1 minus P. So we're going to think about saying, I'm going to give you this for some probability or the worst outcome with some other probability. And if you plot this probability as a function of P, when P is 1, you get the best outcome. So you prefer the lottery. When P is 0, you get the worst outcome. So obviously you prefer the outcome. If you ever prefer the best outcome, so if you ever prefer the lottery, then obviously prefer the lottery when there's a bigger chance of getting what you want, okay? And that argument holds and at some point you have to flip. And that flip is called, the place where you flip is called the utility of outcome, okay? And von Neumann and Morgenstern gave a few intuitive assumptions, and they prefer the outcome if and only if there's a higher expected utility. So if you think about utility, you're always thinking about combines with probability because it's gambling. There's lots of evidence, in particular, from prospect theory, and other people have really challenged it, but it still remains very dominant in artificial intelligence, even though it doesn't necessarily fit how humans think. All right. So before we're talking about time, so let's think about how we do time. So we don't only just things go on and on. So let's think about how you compare the following sequences of rewards per week. You get $1 million today, and then you get 0 forevermore, or you get $1,000 every week. What do people prefer? Well, they're sort of exchangeable. If you have $1 million, you can invest it at 5% and get $1,000 a week. Or if you have $1,000 every week, you can take out a mortgage for $1 million and at 5% interest. So they're sort of exchangeable. They're sort of almost equivalent in reality. Here's a question. So the question is, so now let's think about suppose the agent receives a sequence of rewards in time, what utility should be assigned? Well, you could just sum them all up, although some of the times one of those is infinite and one's 1 million, so obviously the infinite is better. You could average them. Again, the 1,000 has an average reward of 1,000. You get 1 million at the start, you get an average of 0. What we tend to do is we use discounted return. Say, well, the future is not would rather something now than in the future, so we add this discount factor. There's lots of reasons why you might do this. And if you let v of t be the discounted return from time t, you get this formula you've probably seen from reinforcement learning. You think it has something to do with reinforcement learning. No, it has nothing to do with reinforcement learning. It has everything to do with values. What's important to you? Okay, so you should know that when you see this formula, we're talking about what you actually want. Okay, and it's not a hyperparameter to be optimized. I keep saying let's parameterize, let's use this as a hyperparameter. Let's optimize it to get what we want. Well, it's not that. It's about what you actually want. If you don't care what you want, it doesn't matter what you do. But this is something that specifies what your goals should be. Okay, so that's another thing you should know, is that this one here is much more about what you should do. All right. So let's talk about this. Let's extend our belief networks to decision networks. Here's a pretty typical way of actually reasoning under uncertainty. So this is the belief network, and the symptoms depend on the diseases. Okay, these are just random variables, just like we saw before. You got the probability of symptoms given diseases, and then we have these rectangles that are decisions, and the test time here depends only on the symptoms, and then you have test results depend on the test and the diseases, and the treatment. When you're deciding on treatment, all you get to observe is the test results and the symptoms. You have to decide on what treatment to do. The outcome depends on the treatment, and the utility depends on the outcome and the test. And the test could actually be very bad for you, but you're still going to do it because it improves your outcome. What's important here is we can reason about all of these things without ever knowing what the diseases are. And the reason for making any distinction in here is because of the action. Because utility only depends on what you do in the end and what the world is like. Everything else is just for us to work out, in order to work out what the treatment is. All right. For artificial domains, such as games and factory floors, you can observe the state of the world. It's fully observable. And here's the diagram of a fully observable Markov decision process, where the state just depends on the action. Depends on the action and the previous state. And the action, you can get to observe the state. Okay. What to do can describe in terms of this Q function, the value function, the policy. And this is, you've probably seen this, it's all about reinforcement learning, right? Well, not really. Well, you could learn it with learning. So if you have lots of experiential data or a model to generate the data, or in a game you can just generate as much data, it's called reinforcement learning. But you can also do it with planning. You could do search or dynamic programming. In fact, you might have learned dynamic programming is a very abstract problem, but it actually started off as a solution to Markov decision processes, and that was the very first dynamic programming algorithm, was for Markov decision processes. Requires a model. It's called decision theoretic planning, and you think, oh well, everyone does reinforcement learning, and the answer is, well, not really. Nearly everyone does both. So you can do both. So for example, AlphaGo and AlphaZero, the famous ones that for game playing and playing Go and chess, they learn V and Pi, but then they play lots of games. They do lots of search. Okay, so it's very typical that you're going to learn what you can learn, what you have data for, you learn, but everything else you're going to search over it. So it's not a matter of just saying, well, let's use reinforcement learning, but rather let's try and work out how reinforcement learning and planning fit together. One of the things that's true, but not many people know, is it also works, V, Pi, and Q works for partially observable domains. You can use the history instead of the state. And if the agent observes and remembers the relevant history, it's no forgetting. Oh, all right. When is it not no forgetting? Well, it's not no forgetting in something like a multiple agent game. Oh, I'm running out of time. All right. And here's an example of multiple agent game as a soccer penalty kick. I'll skip over this. And you can plot the probability of the kicker kicking right as a function. You can plot the value, the probability of a goal, as the probability of the kicker kicking right, and you end up with this nice function, and this is called the Nash equilibrium. And it's not something you can optimize, that everyone just acts for themselves. You actually have to think about other agents and act randomly. All right, let's skip this one. All right, let's skip this one. I'm running out of time. Anyway, last one is, where do values, goals, and preferences come from? There are two cases that we have to think about. One is where the only impacts of an action are on consenting participants. If you're selecting meals, what should I have for dinner tonight? If you're selecting treatments for the patient, or you're playing a game. All right, this is the easy case, right? What do we do when they're only consenting participants? The other case is the difficult case, is there are non-consenting people and the environment may be impacted. If you're driving a car, there are other people who are impacted because they're pedestrians who could get hurt, and there's pollution and everything else. Building a sewage treatment center is another example. So first is you should be suspicious that tells you what to do without asking what you want. Okay, you've got to be suspicious of something or something that tells you what to do if it doesn't tell you what you want. And lots of apps have very limited alternatives to choose from. So Google Maps, I can choose the start and the mode of transport and a few options. Then it returns a few options that are estimated to minimize time. It doesn't let me do all sorts of other things. It doesn't let me avoid going by my mother's house because then, she'd expect me to come to visit her, or go via the most scenic route, or take the train with some walk, which I wanted to do in Singapore, but I couldn't actually get anything to say. I actually want to take a little walk and then take the train somewhere with one stop. And sometimes things let you say anything, but you don't know what to say. So this is a real problem. Preference elicitation is a really big problem that we see far too little of, and it's an important problem for actually knowing what to do. It's much harder to do when some people are disproportionately impacted. So here's an example that's actually used in every city in the world. They make decisions about where to place their sewage treatment plant. It's a stinky problem. And how much to pay for smell reduction. Okay, people near the plant want the least smelly system. Taxpayers away from the plant want the cheapest option. The majority want the cheapest option because they want to pay a little money. It's only going to impact a few people. And so what you actually should do, and what people actually do to determine this, is they think ignorance is bliss. So what we're going to do is to choose the smell. Let's say, which one would you do? I'm not going to tell you where the sewage treatment plant is, but you now have to work out how much you're going to pay for smell reduction. Again, you're doing a lottery. And everyone is gambling except the people at the top of the hill, or the people at the top of who are the well-off people. They know it won't be near them, so they're not going to want to pay that. But you sort of somehow want to think about how can we get fair decisions when people are disproportionately affected. One solution that they do in Vancouver, where I live, is to have small focus groups and actually discuss people's values. And they inform them about the issues and they discuss options. So finding out preferences is a really difficult problem, and there's lots of social scientists who have thought about this, and we should not ignore what they do. So the real question is the really difficult one, which I don't know how to do, but is an important topic, is how to make it fair when people acting and the people impacted are in different socioeconomic groups, different countries, or even not yet born. So when what you're doing can affect the people who are not yet born, how do we somehow, as a society, decide what to do? This is a nice quote from Barack Obama from 2016. Self-driving cars. What are the values we're going to embed in the cars? There's going to be a bunch of choices that have to be made. The classic problem being, if the car is driving, you can swerve to avoid hitting a pedestrian, but you might hit a wall and kill yourselves. It's a moral decision. And who's setting up these rules? So as a community, we have to work out who's setting up the rules for all of these values. Somehow we need to think about this and not just sort of accept the fact that, someone's given me the preferences, let's just go with it. We need people to think about these preferences. It may not be computer scientists, will probably be social scientists. We have to listen to those when we're building intelligent systems. All right, let's finish up here. So here's some of the things you should learn about on the way of here. And I hope everyone's learned at least one thing. I know I learned a few things while I was writing this that I didn't know before. So agents are judged by their actions. Acting under uncertainty is gambling, and probability is a calculus of gambling. It's impossible to learn the effect of actions from observation to know alone. You need a causal model. So if you want to work out what to do, and you need to act in the world, you need to actually play with the world in order to work out what to do. Determining truth is a realm of science. We're going to use all available evidence, have diverse hypotheses, carry out experiments, and always be open to new evidence and hypotheses. Science isn't only the realm of scientists. We should all be doing this. In everything we do, we should be thinking skeptically about what we're doing. Okay? We should also question what we're doing, build persistent hypotheses that last through time, build evidence for things, mix up all the data in the world. What an agent should do depends on its preferences and others affected by the outcome. What it should do depends on preferences. We can't just as a community ignore preferences. And determining which values to use in our preferences can be established fairly is a major non-technical challenge that we as a community really need to take on much more seriously than we have. And the title again is The Essence of Artificial Intelligence is Action. All right. Thank you. And I've got time for some questions, I think.
Hi.
Can you identify yourself?
Oh, I'm Ken Kahn, retired from Oxford. So the point about it possible to learn from observations, but why can't you learn from observations of other agents acting in the world?
You have to know why they chose the action that they did. Right? So you need to know why they chose those actions. It's the same way of the example of the vaccine, right? If they chose the vaccine because they're in a place where the vaccine was endemic, right? Going to hospital looks really bad. It's correlated with death, but people go to hospital because they're sick, and it's the sickness that kills them typically, right? You have to know why they did the actions.
But with science, you don't do the experiments. You trust the scientists.
Well, the scientists do the experiments.
Yeah.
Well, you build hypotheses. You trust hypotheses that have evidence from lots of data supporting them. We trust the hypotheses because there's lots of data for them. Okay. I mean, the difficult thing about science is that science do the things that they don't know, right? They're always on the frontier of the things they don't know. Whereas there's the body that's in textbooks and things, the stuff they know, right? By science, I mean, condensing things back into the textbooks.
Okay, thanks.
Thanks for the great talk. We have 3 microphones set up. Please come to the microphones and line up and ask questions. And as you're asking questions, please introduce yourself. Thank you.
Hello, my name is David Holmes. I'm at the Mayo Clinic. I wanted to ask questions more on the education side and understand how you take what you talked to us about for about the last 45 minutes and break that into pieces that are accessible and appropriate for students. How do you, because it's not a sequential learning process, right? All these different things you talk about, you actually have to learn a whole bunch of things and then you put together to tell a story, which you did today. So you can talk on the educational side a little bit about how do you break it down?
That's the big challenge of writing a textbook, of sequentializing everything. We try to build things from the bottom up, of foundations for which we can build things and build them up. One of the things we've tried to do is to make things that everything is part of the coherent picture. So everything is part of the coherent picture of what we're doing. So you're not learning things like, oh, we didn't mean this, we're going to throw this away. We're trying to build something so that we're keep building the foundations for doing this. And there's lots of foundations that you need, from logic and probability at the very basic of this, machine learning, decision analysis, relational things depending on what you want. I know people use our book from all sorts of different angles of starting things, but when we tried to do it, we tried to say, what are the things that you need to know first before doing this, and then things build up on top of that. But writing a textbook is fun. It takes decades after a while. It takes a long time to sit and do things and build but you actually learn lots of doing things. Teaching is important too. So you want to think about building from the foundations of building steps by steps, and instead of saying, oh, here's large language models, let's learn those, as opposed to learning the foundations, which it's the next just step about, you could probably invent them yourselves when you know the foundations about what the building blocks are. Thanks.
Hi, thanks for the amazing talk. My name is Abhishek. I'm a scientist at Amazon. I think I have a very vague-ish question. So I like this emphasis on causality and trying to think through about the action making and so on. Whereas if I look at like traditional literature on, even in the beginning when you showed off all this Markov decision process and how beliefs and actions and so on affect. Is there like a theory of how to understand how causality fits into that framework, where like you also choose what actions to take in order to learn the world and so forth? And is that part of your textbook, and is that where we
Yeah,
start?
we have a whole chapter on causality. Taken a lot from Pearl's work, Peter Pearl's work, and other work of trying to build causal graphs that make predictions of actions. So a causal model predicts what an intervention is doing. So you can build up that from the notions of probability theory, and it's all about acting in the world, and there's all sorts of axioms. There's a huge field of this, a subfield of causality that's not separate from what we do, but rather part of what I want to do is saying there's all of these different aspects that come in that we really need to think about in order to build there's all these different aspects that we need to build intelligent agents and machines. Causality is really important. Everyone should know about causality. Read our book, then you can read Pearl's book afterwards. Ours is sort of hopefully a more readable summary. Yeah.
Hello, I'm Stephen Jones from the IQM Research Institute. I really appreciated your sewage plant example. I think it pretty much applies to intrinsic motivation in the agents that we design. I mean, that's what you're saying. With the values we instill in agents, I come with those sort of already, but I pick them for a reinforcement learning agent or some other agent with intrinsic motivation. Could you give me advice on how to not build the sewage plant in a bad place effectively?
It depends on your values. I don't know, bad place depends on what values you have and what you're doing, so how much people do it. It's a sewage treatment plant is one where it's actually a real example. People really do it in the world, and
If I may, like an intrinsic reward based purely on empowerment, for example, that's really good for exploration, but there might be unforeseen consequences. However, it's very popular right now. That's the kind of thing I need advice on.
you need to worry about the side effects of all these other people all these other things that might affect it. It's a difficult problem. One of the reasons I put it up there is it's actually a really tricky problem. I don't know the solutions to it. Unfortunately, there's not a big community of people. Well, there are lots of people working on preference solicitation. We need more of this because people like you are doing this. So part of what I'm advocating here is that we need more people to think about these big picture items, about these issues that I've talked about. So I don't necessarily know the answer to that. I just know that we need to think about it. It's really a social science. You should ask the social scientists, not the computer scientists. We tend to just talk to the computer scientists, but we really need to talk to the other people who know about decision-making and values and ethics and everything else. It's a big problem, but there seems to be lots of money in AI, but we're spending it on funny things, if you ask me.
Thank you very much. Let's thank our speaker one more time and congratulate them on the award.